Hello and a very good morning to everyone from the International Energy Agency in Paris. It's a real pleasure to be here with you this morning and present some of the key findings of our recent report on the role of critical minerals in clean energy transitions. Jumping right in, first, our starting point. Over the last year, we've seen the emergence of several pledges to reach net zero emissions by mid century or shortly thereafter. More than 40 countries and the European Union have now committed to this goal. These countries represent around 70% of today's global GDP and emissions. If these pledges are followed through, this implies a massive acceleration in clean energy deployment. That means a lot more electric vehicles, wind turbines, solar panels, electricity transmission and distribution lines, which are all essential to move us onto a more sustainable path and avoid the severe impacts of climate change. But this also means that a lot more of the minerals and metals that go into these technologies will be needed. Lithium, nickel, cobalt, manganese, and graphite are crucial to battery performance, longevity, and energy density. Rare earth elements are required for permanent magnets that are vital for wind turbines and EV motors. Solar panels are not very mineral intensive as such, but the sheer size of the future solar market means plenty of additional demand for silicon, silver, and copper. And the infrastructure of a cleaner and more electrified energy system is equally important. The expansion of electricity grids needs a huge amount of copper and aluminium. Many technologies that we will need for a clean energy future require significantly more minerals than their fossil fuel based counterparts. It is indeed striking to see the changes in mineral use implied by energy transitions. A typical electric car requires 6 times the mineral inputs of a conventional car, and an offshore wind plant requires 13 times more mineral resources than a similarly sized gas fired power plant. Over the last 10 years, renewables have started to dominate investment in power generation, and as a result, the average amount of minerals needed for a new unit of power generation capacity has increased by 50%. The world has enough resources to make the energy transitions work, but that is no guarantee that supplies of these metals and minerals will be available when and where we need them at an affordable price. Minerals are becoming an increasingly important part of the energy debate and of global energy security. The challenges that they pose in energy transitions are manageable, but require early attention from policymakers to make sure that transitions can be secure, sustainable, and rapid. So, how fast could mineral demand rise? We conducted a detailed assessment of different scenarios and technology evolution pathways, and the short answer is that a concerted effort to reach global climate goals will imply at least a quadrupling of overall mineral requirements for clean energy technologies by 2040. That's the outcome of our sustainable development scenario, a scenario consistent with the Paris Agreement. An even faster transition to hit net zero globally by 2050 would require 6 times more mineral inputs in 2040 than today. The main factor behind this increase is an explosive growth in mineral demand for EVs and battery storage, closely followed by mineral needs for expanding electricity networks, and then the growth of low carbon power generation. Looking in more detail, we see that for some minerals, growth is much faster than the 4 to 6 times. In a climate-driven scenario, demand for lithium in particular sees very rapid growth. It varies depending on the precise strength of climate policies and the technology pathways selected. But in a scenario compatible with the Paris Agreement, the demand for lithium is more than 40 times higher than today by 2040, followed by graphite, cobalt, and nickel at around 20 to 25 times. There are two important consequences of this demand picture. First, it means that the energy sector is becoming a major source of demand for these minerals, which hasn't traditionally been the case. Taking lithium, for example, 10 years ago, the demand for lithium for energy-related applications was minimal. Already today, EVs and battery storage have displaced consumer electronics to become the largest consumer of lithium. And if we get on a trajectory consistent with the Paris Agreement, then by 2040, about 90% of the global lithium supply will go to the energy sector. And the upward trend for other minerals is not quite as dramatic, but shows a similar rise. The second implication relates to the cost structure of producing the clean energy technologies themselves. Technology learning and economies of scale are bringing down the costs of key energy technologies. But as this happens, this also means that raw material costs now account for a larger share of the total. Batteries are once again a good example here. They are much cheaper now than they were 5 years ago, but raw materials now account for some 50 to 70% of total battery costs, which is up considerably from where they were. Higher or more volatile mineral prices could therefore have a significant effect on the costs of transforming our energy system. Turning in more detail to the supply side of the equation, each supply chain has its own complexities, but it's essential to note that the production of many of these energy transition minerals is more concentrated than those of oil or natural gas. These high levels of concentration, compounded by complex supply chains, increase the risk that could arise from physical disruption, trade restrictions, or other developments in major producing countries. For lithium, cobalt, and rare earth elements, the world's top three producing nations control well over 3/4 of the global output. In some cases, a single country is responsible for around half of the worldwide production. The Democratic Republic of the Congo accounts for 70% of global cobalt production, while China is responsible for some 60% of global production of rare earth elements. When it comes to processing and refining operations, the level of concentration is even more notable, with China the decisive player in many of these areas. So, if mineral demand picks up quickly, as it will do if today's climate pledges get turned into actions, will supply be in a position to respond? In essence, as things stand, the production outlook is geared towards a world of gradual and insufficient action on climate change. In other words, investors and suppliers do not yet appear to be convinced that the world's policymakers are going to turn their ambitious targets into action. So we see a looming mismatch between the world's strengthened climate ambitions and the supply of the critical minerals that are essential to realizing those ambitions. For example, in a scenario consistent with climate goals, expected supply of lithium and cobalt from existing mines and projects under construction meet only about half of the projected requirements by 2030. One key precondition to narrow this gap is for policymakers to make clear not just their long-term goals, but also fill in the details on how they plan to get there. That means clear milestones for action and for near-term clean energy deployment this decade. This will be vital to reduce investment risks and encourage capital flow to new projects. The ability of supply to keep pace with an acceleration in energy transitions should not be taken for granted. So I would like to conclude the presentation with 6 key recommendations from the IEA. First, measures to support adequate investment in diversified sources of supply. As mentioned, early and clear signals from policymakers are critical to give companies the confidence that they need to commit to new supply. But security of supply also lies in diversity of supply. In this context, resource-owning governments can support new project development by reinforcing national geographical surveys, streamlining permitting procedures to shorten lead times, providing financing support to de-risk projects. But a comprehensive approach cannot focus solely on supply. It's vital for governments to step up for technology innovation, which can alleviate the strains on supply by reducing mineral intensities and opening up possibilities for substitution. Just to give an example, 40 to 50% reductions in the use of silver and silicon in solar cells over the past decade have been critical to enable the spectacular rise that we are seeing in solar PV deployment today. A third area that's set to become much more important in the future is recycling. Recycling is well established for some bulk metals like steel and aluminum and copper, but this is not yet the case for others, such as lithium and rare earth elements. This will have to change. as the amount of spent EV batteries reaching the end of their first life surges after 2030, with the opportunities largest in countries and regions that have seen large and early deployment of clean energy technologies. Recycling these volumes won't eliminate the need for continued investment in new supplies, but we estimate that by 2040, recycled quantities of copper, lithium, nickel, and cobalt from spent batteries could reduce combined primary supply requirements for these minerals by around 10%. The fourth area encompasses measures to increase the resilience of supply chains and improve market transparency. Regular market assessments, good data, and periodic stress tests can help policymakers identify possible weak points, evaluate potential impacts, and devise the necessary responses. Strategic stockpiling can, in some cases, also help countries weather the short-term supply disruptions. The world also needs to step up efforts to tackle the environmental and social impacts of mineral developments, including the emissions, local pollution, the treatment of worker safety and welfare. Solutions to climate change cannot work on the back of injustices or poor environmental performance further up the value chain. And finally, we need to strengthen international collaboration between producers and consumers. An overarching international framework for dialogue and policy coordination among producers and consumers can play a vital role. There are huge opportunities here if governments can act and act together. For our part, the IEA is determined to play a leading role in helping governments around the world to anticipate and navigate potential vulnerabilities and avoid damaging outcomes for our economies and our planet.